Hi, everyone. We're going to begin. My name is Mohammed Mamdani. I am the director of T-CAIREM, and it is my pleasure to welcome you to the Temerty Center Speaker Series. I just want to start off by acknowledging that this land on which the University of Toronto operates, for thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. The Temerty Center for AI Research and Education in Medicine, or T-CAIREM, at the University of Toronto has been made possible by the generous donation of the Temerty family. We are an interdepartmental center that serves a focal point for collaboration between healthcare providers, trainees, researchers, computer scientists, engineers, and industry to advance health through artificial intelligence. And our goal is to transform healthcare through AI. Pretty lofty goal. Just want to quickly mention that this event is CPD accredited. To obtain your CPD credit, please complete the evaluation form that we will email to all attendees following the event. And don't forget to provide your name and email address on the evaluation form. That's pretty important. And a note to the attendees, please use the Q&A function in Zoom to submit your questions for Dr. Krishnan. Dr. Krishnan will try and address them during the discussion portion of this webinar, which follows immediately after his talk. And it is my great pleasure to welcome Dr. Rahul Krishnan. I want to just provide a quick overview. He is an assistant professor of computer science and medicine with the Department of Laboratory Medicine and Pathology, or LMP, at the Temerty Faculty of Medicine. He is a member of the Vector Institute, where he holds a CIFAR AI Chair, one of the very prestigious chairs nationally. His research has developed new algorithms for probabilistic inference and applied machine learning to problems in healthcare, such as modeling disease progression and risk stratification. He received his MS from New York University and his PhD in computer science from MIT in 2020. We're very, very fortunate for Dr. Krishnan to join our University of Toronto community, and we're really looking forward to the incredible things that he's going to be doing with us over the next few years. And I'd like to now hand it over to Dr. Krishnan, who's going to be giving some really interesting talk on machine learning for chronic disease management. Thank you, Dr. Krishnan.
Thanks so much for the kind introduction, Mohammed. It's wonderful to be here. I should add that in addition to my graduate degrees, I actually did my undergraduate degree in Toronto, so it's great to be back and arguably a different capacity. So today, I'm going to tell you about some of the work that I have been doing over the last several years, both as part of my PhD and during a year where I worked at Microsoft, on this topic of the application of machine learning for chronic disease management. And so I often like to put out this disclaimer here, which is important to me because I think as this intersectional field grows more and more popular, we need to be more careful about some of the statements that we make. And so I'm going to say that the contents of this talk should not be interpreted as medical advice. And so I'm going to talk to you about how to apply machine learning algorithms to clinical data, but the outputs of the algorithm do need to go through the entire pipeline of validation before they're taken to use in clinical practice. And so with that, what I'm going to talk to you today is about this idea of making use of machine learning in chronic disease management. So I'll introduce the problem. In the first act of the talk, I'll talk about modeling the progression of disease biomarkers in the context of multiple myeloma, which is a rare and incurable cancer. And in the second part of the talk, I'll talk to you about self-supervised learning for histopathological data. And so these two ideas seem seemingly unrelated, but they're really tied together by this notion of the fact that as we go across time in recent days, what we're finding is that we're collecting a large amount of data about patients. So this data can include anything from medical images, inpatient health monitors, examination, patient notes, and laboratory results. And this data bears an important question, which is, what can we do with it? And so what people have done with it in the past is try and identify statistical patterns that exist and make use of regularities in those patterns in terms of trying to understand diseases better. as well as develop software tools that clinicians can use as part of their day-to-day workflow to try and improve the speed, efficiency at which they can complete tasks. So in this story, the vision sounds promising, but the reality is a little harder because clinical data is incredibly complex. If we think about it from a humanistic perspective, we have data at multiple different scales of the human body. At the very lowest level, we might have data on human genetics. If we go one level up, we might have imaging data, which give us a view into the patient's organ systems. We might have laboratory test measurements, which give us a different view into how the patient's organ systems are functioning. We have clinical notes, which provide, to some degree, subjective assessments of patients as they enter and leave hospital systems. And finally, we have population level statistics that are aggregated and collected by agencies that track infectious diseases across time. And so these data modalities span multiple scales of the human body, and they also often span time, which correlates in many cases, particularly in the context of chronic diseases, to the severity of the disease. And so the question that machine learning and the subfield of machine learning for healthcare asks is, how can we build models to capture this complex kind of data? And I'm not going to talk to you about all of these kinds of data modalities today. I'm just going to focus on lab tests in the first portion of the talk and imaging in the second portion of the talk. So one tool, and the next few slides will maybe introduce some of the technical material that we will make use of in this talk for those of you who are less familiar with some of the tools that are used in machine learning. We'll make use of ideas from a subfield of computer science known as deep learning. And so deep learning is this idea that if you have an object that you care about making predictions from, then the best way to make predictions from that object is to learn what features are relevant. And the way that deep learning does this is that it constructs multiple levels of what are known as feature extractors. So in this case, in this image that you see over here, if you wanted to classify whether the image on the left was a dog or a boat, then you might make use of such a deep neural network. And you would make use of multiple layers of convolution and max pooling. And at every subsequent layer, you would learn less and less granular features about the image, which at the very top layer will give you an assessment of the kinds of objects that are in that image. And so when you see this fully connected at the very end, that could represent a vector of numbers that summarizes what the model has assessed to, that the image contains. For example, one of those numbers could represent whether or not the image contains a boat, which would be the final output of your model. And so one idea that I want you to take away from this slide is the idea that deep neural networks construct iterative feature extractors, and these feature extractors are not just useful for the tasks that they were trained on, they're often going to be used in multiple different tasks. And so what's really driven some of the advances in the context of deep learning in the last several years is this idea of automated feature extraction. And so it doesn't matter what kind of event that you are interested in classifying, these models are particularly good at detecting patterns. So at the bottom layer, they might detect edge filters. At the middle layer, they might detect compositional parts of edges, which compose, if you were detecting faces, it might compose an eye or a nose. And at the top layer, it represents regular patterns that you've found in your data set. And in the context of neuroscience, people have studied these kinds of filters and assessed that similar kinds of neural circuitry is responsible for how our eyes interpret image. And so deep learning has really driven a lot of the advances in computer vision in the last few years. But in this talk, we'll talk about computer vision in the latter half, but we'll also talk about using these ideas from deep learning in the context of modeling clinical data. So what does that look like? So I'm going to use the random variable x to denote a clinical variable, but in this context, it is essentially a large vector representation of a patient's data. So if we were thinking about a patient who is suffering from a chronic disease like multiple myeloma, the vector representation of that patient's data would look like something like this, where the first dimension of that vector would represent the level of IgG in this patient. Perhaps one of the middle dimensions would represent the level of IgA and their serum M protein. And so when we think about doing machine learning on high dimensional data, we need a way to represent the data. And these vectors X are vector representations of that data. And the same goes for images. So when we denote with X an image, what we're really saying is that we're going to take that square image, we're going to flatten it, and we're going to put all of the values of the pixel that correspond to that image in different parts of this vector. And then once we have this vector, we can go back to some of the previous slides and learn machine learning algorithms on it to solve predictive problems. And so along the way, this idea of a representation is going to be relevant, because what we're going to do is want to transform our high dimensional data, this high dimensional X of clinical covariates, or this high dimensional X of images, into a much lower dimensional representation. And so I'm going to denote that by Z, and other works have different representations for this, but think of this as just a small set of numbers that captures the relevant patterns that you really care about knowing in your data set. And so Z, for example, in the image of whether or not there's a boat in the image could be the probability of there being a boat in dimension 1. And so these are just some very fundamental concepts that are going to be relevant as we go through the remainder of this talk that I wanted everyone to have access to. And so in a slide, machine learning maybe follows these 3 steps. You collect the X's that you care about modeling for any problem. You're going to do some computation on it, which is going to be learning a machine learning model using the data. And the goal of any good machine learning model is going to be the ability to predict outcomes well on unseen data. And so the reason you want your model to satisfy this property, which is known as generalization, is that you want to be able to trust that when you put this model into a software tool that you then deploy in the clinic or you then deploy in the wild, you'd like it to continue to perform regularly. You'd like it to have learned the truly interesting patterns in your data when it's making predictions so that it generalizes well. So these are some this is maybe ML 101 in 4 slides, which I admit is not very satisfactory, but it sets you up for what I'm going to talk about next. So in the next 20 minutes, what I'll talk about is this idea that we can make use of these tools from deep learning, as well as a much older field of Bayesian networks, in order to develop machine learning models of high dimensional clinical biomarkers. And so we'll start off by talking about unsupervised learning of time series data. And in the second part of the talk, we'll talk about machine learning models of gigapixel histopathological images. So let's start with Act 1, and this is a collaboration that was led by Zishan Hussain, who's a third-year MD PhD candidate at MIT. And this work was published at this year's ICML. And so it's called Neural Pharmacodynamic State Space Modeling. And really, one of the motivating factors that led us to think about this work was this picture. So one summer we were all sitting together and we decided to draw on the whiteboard a oversimplified view of how many chronic diseases might be treated. And so that's what this cartoon essentially represents. So on the x-axis, you have something like time for a single patient. And on the y-axis is a latent or unknown notion of disease burden. And so the reason I say that it's latent is because for many chronic diseases, you often don't observe symptoms of that disease until the disease burden crosses a certain threshold, even if it does exist in the patient. And so what's denoted by the first event here is the idea that when the patient realizes something is wrong, they might go to the doctor and they're diagnosed. And so the doctor might put them on the first line of therapy, which is a sequence of medications that are commonly derived from clinical trials that have been known to work well for a wide variety of patients. And it's the first thing that the clinician might suggest to this patient who's suffering from a chronic disease. And so let's ground this chronic disease in the context of multiple myeloma. And so if the patient is diagnosed with multiple myeloma, they would have a first-line therapy. This first-line therapy might work, at least for this patient it does initially, but at some point in time, this therapy stops working. And they have an event that's known as relapse. And so relapse is when the first-line therapy fails, and at that point in time, the clinician moves on to the second line of therapy, the third line of therapy, and eventually for diseases that are incurable, such as multiple myeloma, death. What this picture told us is that there's interesting regularity in the treatment protocols that exist for chronic diseases. And this is not just in the context of multiple myeloma. There's a broad field in biostatistics known as chronic disease management. And this chronic disease management model is what I've presented a cartoon visualization of. And so a valid question that you might have here is, well, why do you think machine learning can help here? And so when we were sitting together and brainstorming on the whiteboard, an initial assessment of this, an initial attempt at an answer to this question is essentially that something that was given to us by our clinical collaborator, which is that knowing the trajectory of a patient early on could help inform the choice to provide aggressive treatment or not in the early stages of the disease. And so in the context of multiple myeloma, where the disease is treated via combination therapy, which is a cocktail of drugs that are prescribed, there might be two different choices of which cocktail to provide. And the choice of which cocktail to provide may not always be deterministically known in the clinical community. And so in multiple myeloma, there's uncertainty around which is the right choice. And for an individual patient, depending on their unique characteristics, doctors, our clinical collaborator mentioned that it might be that they respond better to treatment A, which is what actually happened, and we observe a progression as a consequence of that. But their disease burden might have been much lower had we put them on the protocol B. We just never know that outcome because we never prescribed that treatment for this specific patient. And the argument that I'm trying to build up to here is that if one has access to a very, very large database of prior treatment history, as well as potentially clinical trials, how can we use machine learning models to think about automating this vision, which is automating the ability to provide first-line treatment assessments for patients who suffer from chronic diseases? So this vision is, as of this point, a little far away, but the work that we did was in the context of a very, very small part of this vision, which is the development of machine learning models to forecast the initial trajectory of patients who suffer from chronic diseases. And so what we have at hand is retrospective data from electronic health records that look a lot like this cartoon picture. So in this cartoon picture, you have some baseline statistics, which correspond to the at diagnosis state of the patient. So this could be the genetics, the demographics, the baseline set of lab values that are often taken as a standard panel when the patient is admitted for treatment for this chronic disease. And then you have a certain set of time varying features. And for a lot of diseases, this could be treatments, which could be multivariate, as well as the annotation of the line of therapy, as well as biomarkers such as lab 1 and lab 2, which in the context of multiple myeloma could be serum IgG and serum IgA. We don't always observe the treatments over time, and so these red points denote that they may be missing. But at the end of the day, what we have is a collection for multiple different patients, and this visualization is for a single patient I. We have maybe N patients in our data set, and for all of them, we have data that looks like this cartoon. And so the mini problem in this broad vision that we tackle in this context of this work is that of doing good unsupervised learning of clinical biomarkers conditional on a patient's treatment regimen and baseline data. So we're going to say that we have access to the baseline B as well as time varying treatments U1 and U2 into the future for at least, say, the initial lines of therapy. And so the argument is that given access to the doctor's initial plan, can we build good models for this piece, the time varying biomarkers that serve as a proxy for the underlying disease burden of a patient? And so once again, I'm going to hill back to the way in which this representation behaves. And so I'm going to say that x1 denotes the time, the lab values at time step 1, and x2 denotes the lab values at time step 2, which in this case, according to this picture, they don't change over time, but in general, they will. And so what we want to do is build models of how x1 and x2 change over time, which is what you see in the bottom right of this model here. And the class of models that we're going to make use of are what's called latent variable models. So latent variable models, of which most of you may have heard of a latent variable model known as the hidden Markov model, are a rich and powerful class of models of time-varying data. And so in particular, what this latent variable model is saying is that there is some latent representation of the patient that changes with time, and that change is going to be affected by the treatments that are given at each point in time. And at every point in time, the high dimensional biomarkers, x1, x2, of which we saw examples in the previous slide, are going to be determined by a low dimensional state of numbers. So remember, in machine learning, we like to use representations, and these representations are just a small summary statistics of the latent characteristics of this patient. And so this is an example of, say, a Gaussian state space model if we assume that the distribution of Z1, Z2, Z3 is a normal distribution. And so this time-varying latent process is something that we can imagine represents the latent disease burden of the patient. This was, remember, the motivating picture that we brainstormed and thought about when we talked about chronic disease management. And so if we think about what existing approaches have used in the context of this class of models, they've often been linear. And so this notion of linearity can often be a limitation. And so if you were to naively consider a more complex class of models by making the functional relationships between these random variables nonlinear, then one issue that we run into is overfitting, which is that the complexity is often very difficult to control in the context of learning this class of models on disease cohorts. And so the approach that we took for this class of the model, and there's a bunch of math here, which if you're interested, please do read, but it is not relevant to understand the key points of this talk. The approach that we took is really to think hard about the kind of domain knowledge that may be relevant to how the latent disease burden in a patient transitions over time. And so the kinds of disease burden that we imagine transition in a patient, we think that the disease burden is going to be affected by an individual's line of therapy, that is which line they're on, line 1, line 2, or line 3, as well as this notion of mechanism of drug effect. And so this seems like a slightly different idea. So in order to understand how we made use of mechanism of drug effect, we turned to a subfield known as pharmacokinetics and pharmacodynamics. So what we wanted, remember, I told you that one of the pathologies that current nonlinear state space models face when trying to model the density of data is the fact that they would overfit. And so to limit that overfitting, we wanted to make use of domain knowledge that we could incorporate into the model to reduce the bias that the model might have in the way that it estimates the time-varying dynamics that we observe over time. And so we turned to PK/PD modeling as a way to give us inspiration on the kinds of domain knowledge that we could then incorporate into this nonlinear model. So one of the challenges that we faced was that traditional approaches to PK/PD modeling typically made use of a single intervention and a single biomarker. But what we were really interested in was the response of the latent space, which ideally corresponds to this disease burden. And we wanted to know how this multidimensional latent space responded to the multidimensional set of interventions that we were being prescribed. So imagine you're a multiple myeloma patient, the first line of therapy is KRD, and you get KRD in the first time step and just RD in the next time step. We wanted to think about functional classes that could characterize how the latent state of this patient might change through the prescription of these groups of drugs. And so we wanted to build these simple parametric functions that operate on the latent space and capture a part of the treatment mechanism. So this was really the cartoon that we had in mind when we made this kind of model. And so we developed a neural architecture that in one dimensions looks like this, where it, by varying the parameter rho, which is a function of the previous latent state, you could capture the fact that a latent state or the underlying disease burden of a patient could rapidly evolve over time and then diminish with each line of therapy. And so on the left-hand side, what you see are various kinds of plots that this choice of dynamics is able to capture over time. And remember, this is dynamics that are happening in the latent space, which we hypothesize correspond to the underlying disease burden of the patient. And so this class of models, of which I've shown you one, represents the slow gradual relapse after initial therapy in a line of treatment. And that was one example of G1 that we developed. And so in the paper, we showed 3 different examples of G1, G2, and G3, which we aggregated and incorporated into an attention mechanism, which is a mechanism by which which is a mechanism in deep learning that allows you to adaptively select which function is appropriate at any given point in time to incorporate into the transition function of this state space model. So remember, the big picture here is that we want to learn a nonlinear state space model. The current approach is overfit. We wanted to incorporate domain knowledge. We developed neural PKPD models as domain knowledge, and we incorporated them into the transition matrix of these state space models. And in terms of evaluating this model, we took a data set of patients from the Multiple Myeloma Research Foundation COMPASS study. And so this study was a prospective cohort of individuals who were tracked from the point of diagnosis all the way to the point at which they either died or left the study. And it gave us data on how they behaved over time in terms of their clinical covariates, as well as the treatments that were prescribed. And so just for the purposes of time, I'm not going to go into the details of what X contained and what U contained, although you can find that in the paper. I'm just going to highlight 3 of the key takeaways. So the way in which unsupervised learning models are evaluated is via a number known as a negative evidence lower bound, or the NELBO, or the negative log likelihood. And so they're in many ways related. And so a lower number represents a model that has generalized well. And so when we look at the test NELBO or test NLL, what this is telling us is that the choice of this parameterization for the state space model results in a state space model that generalizes the best on this cohort of, on this real world data cohort of multiple myeloma patients. I see there's a question in chat, which I'm happy to take. Okay, sorry, the hand is no longer raised, so I'll continue. And so one of the most popular classes of models for modeling the progression of data is the state space, is a linear state space model. And so when we compare how a linear model does on this data set, what we find is that it doesn't have the representational capacity to capture some of the subtleties of the dynamics of these biomarkers over time. However, when we look at nonlinear classes of models, whether they're recurrent neural networks in the form of GRUs or nonlinear parameterizations of state space models, we find that they overfit, which is that they get a very low training accuracy, but their test performance is poor. So they have very high negative evidence lower bounds or negative log likelihoods. And so we motivated this choice of model by asking a clinician, what would you do if you had access to this data? And they said maybe you could use it to forecast how patients behave in the initial points of time during their treatment for this disease. And so that's exactly what this particular plot is trying to show. What we're going to assume is that we observe data up to time point 10, and we predict data into the future using two classes of models. In the orange dotted lines is the linear model, and in the lines in black with the black dots is the PKPD model that uses the neural parameterization of these PKPD functions. And in blue, the dots that you see over here are what the true data look like. And these are never seen by the model when it's making these predictions over time. For these two serums, serum IgG as well as serum lambda, we've normalized the lab values over time so that the healthy maximums and minimums fall between 0 and -1. This was an arbitrary choice, and you can consider different choices, but effectively it represents scalings of where these lab values lie on the y-axis. And what this particular plot is showing is that the use of this neural architecture realizes models that allow you to forecast and fit the real data much better, even though it doesn't know what's going to happen to this patient when forecasting forward in time. And so, this is maybe a good point to conclude Act 1, which is to summarize. And so to say that we've developed this new attention-based neural architecture that's inspired by pharmacology that captures the response of drug combinations in representation or latent space, and that the use of this neural architecture allows nonlinear state-space models to generalize well when data is scarce. I would say that one of the limitations of this model right now is that we've only evaluated it in the context of the cohort from the Multiple Myeloma Research Foundation. I think it's important to study this state-space model on bigger and more diverse cohorts to ensure that the performance that we see is meaningful. And so Graham says in the chat, designing parametric functions that operate on latent spaces is something that's non-obvious to me because we often think of latent spaces as high dimensional and complex and not in descriptive terms like input space. I think it's intriguing that a latent space became your hook for domain knowledge. Do you have a conceptual breakthrough for this point, or were you translators between real concepts and something as abstract as a latent space? So this is a great question. I think, in statistics and machine learning, there's a long history of leveraging domain knowledge in clever ways in order to build learning algorithms that generalize well when data is scarce. I would say that this work is an example of that. I don't yet know whether I don't yet know that we have a theoretical proof to show that there are choices of neural architectures for which we can always guarantee that we get better generalization from the choice that we made. But I think that's an interesting question to explore in much, much more controlled synthetic settings. And so I'd say that there's a lot of this work points to a lot of intriguing work. Theoretically, it points to thinking about how we can map perhaps the true underlying causal knowledge of how these biomarkers evolve in terms of parameterizations of state-space model and what the consequences of that are on the sample complexity of learning. Practically, what this is saying is that you should often work with domain experts when you try and do the exercise of building these kinds of models, because sometimes the insights that they have can be translated into language that they're familiar with, from language that they're familiar with into parametric functions that you would then use some of the tools in machine learning like autodiff to automatically learn. And so that this really was an example of the latter, where we talked to the doctor and they mentioned that one of the ways that for a lot of these drugs in the context of multiple myeloma, the true underlying effect function is unknown, which is to say that people have conducted RCTs to show their efficacy, but the exact mechanism on which they operate is not always known. And so that's what motivated us to consider the possibility that perhaps an ensemble of different neural PKPD functions, as we did in this work, might be a reasonable approximation to different kinds of treatment effect functions. And so in the context of this future work, it's important to go back to the initial vision and ask, where does this fit in this vision for what one would like to be able to do with the treatment and developing software for chronic disease management. And I think there's a lot of really interesting work in this space. One interesting line of work is thinking about how to enable tools to do automated counterfactual inference from large-scale registry data sets. And so in this particular data set, in the Multiple Myeloma Research Foundation COMPASS data set, the treatment assignment is not random. And so it's for each patient, you're not flipping a coin to provide them treatment. And so the consequence of that is that you cannot use this model naively if you wanted to ask counterfactual queries. You need to be a little more careful and correct for the selection bias due to the non-randomness of treatment assignment before you do that. The other problem that comes about often in the context of disease progression is that positivity, which is the condition that you always have a non-zero probability of seeing people who have different treatment assignments, is not always going to be guaranteed as you go further in time. It might be guaranteed in the beginning when there's a lot of patients for whom you have that are very similar, for whom you see different treatment options being played out. But as you go later and later in time, the number of samples of patients who survive in the very late stages is very small. And so positivity diminishes there. And so we need new technical solutions, either in the form of assumptions for causal inference or data aggregation solutions that leverage statistical strength from different data sets in order to try and tackle these problems, while continuing to think about how to learn these flexible model families in order to capture the nonlinearity that exists in the data. And so another line of future work that we're thinking of using this model for is as a simulator for reinforcement learning. So if we find satisfactory solutions to the above two problems in the context of treatment assignment and positivity, we can think of this model as a proxy for what would happen to the patient. And so in reality, one of the challenges of doing reinforcement learning in a space like healthcare is that we cannot experiment on people. But if we have a good model of how people behave and react to medications, perhaps we could use that model as a proxy, as a simulator for the development of policy functions from reinforcement learning. And so that is another question chat, but maybe I'll keep that for the purposes of time to the very end. And so I want to move on to Act 2 of this talk, which is about a different data modality that is often used in the treatment and care of cancers, which is histopathological image data. And so a lot of this work was led by my intern at Microsoft, Richard Chen, who's a third-year PhD candidate at Howard University and Brigham Women's Hospital. So histopathological images are interesting because when you think about a lot of problems and tools that have been developed for the machine learning community, they've been developed for 256 by 256 dimensional images, such as CIFAR, ImageNet, and so on. Histopathological images are massive. They span like an average H&E image, which has been H&E slide image, which has then been digitized, will be about 10 gigabytes in size, and it would have 200,000 by 300,000 dimensions. So the field of histopathology has existed for the microscopic examination of tissue to study diseases and their presentations. So the pipeline is something like this. You'd have a surgery, a biopsy, or an autopsy for the excision of tissue. You would be, the tissue is then placed in a solution to stabilize it and prevent decomposition and to enhance some of the cellular regularities that pathologists look for. And you would investigate these tissue samples under a microscope. More recently, what's been done to the tissue samples is that they've also been digitized. And it's these digital images that we're going to talk about in the next 20 minutes that constitute H&E images. And these images are routinely used for the diagnosis of cancer. But the key question is, how can we use machine learning algorithms to think about building representations for for histopathological image data? So remember, in the previous part of the talk, we talked about building this latent representation that represents a patient's disease burden. We can ask the same question in the context of an image, which is no longer time varying, but rather static. We can ask the question of, can we come up with this vector of numbers which captures interesting substructure that exists in this image? And so what's been done in the past are these two big approaches called weakly supervised learning. And so on the top is an example of making use of nucleic segmentations to build graphs, which are then fed into a graph convolutional neural network. And if you don't know what that is, just think of it as a neural network that takes as input this graph and captures relationships that allow you to capture correlations in common graph structures across the board in the image. And the output of this model is whether or not a tissue sample contains cancerous or is entirely benign. And so this kind of a model, if built successfully, can be used for classification, for detection, for risk stratification, and for treatment response prediction. And so another class of learning method that has been applied to histopathological images is that of multiple instance learning. And so the idea in multiple instance learning is you have your big 200,000 by 300,000 dimensional slide. You chop it up into tiny, tiny chunks, each of which is 256 by 256 to form the stack of patches. And you feed each patch into an encoder to get a bag of representations, so one representation for each patch, and you feed that into a multiple instance learning algorithm. And essentially, there's many different multiple instance learning algorithms. Some of them might simply take the average of the representations. Some might take the weighted average of these representations. But many of these different algorithms are variants on a theme of how do I take a bag of representations and convert it to a single representation that I then use to make predictions from. And so it's been shown that for many of the existing approaches with weakly supervised learning, you have a lot of really cool insights that the models learn automatically. So the attention weights in the context of some of the weakly supervised learning algorithms that have been tried in the past automatically localize tumor regions in binary classification tasks of benign or metastasis. And what that's saying is a facet of the model is capable of giving you a localized version of where there's a benign or metastatic tumor in the histopathological image, which is interesting because it's something that the model did not have access to when it was learning, but it learned to annotate those regions as part of the training algorithm. And so the slide has a lot of information on it, but I think the key takeaway here is that in existing work, the current paradigm is often going to be limited by clinical domain knowledge. And so we're going to need, and so remember in the machine learning pipeline, we have data set construction, which is one of the most difficult phases in computational histopathology because it requires clinician input at every stage. We need labeled images in whole slide images with known morphological phenotypes, which are known as patch level tasks. And we need subjective and prognostic decisions that are made from the entire whole slide image, so slide level annotations. And so what Richard and I were talking through over the summer was how can we identify new phenotypic biomarkers and what's missing in current decision making that can help guide prognosis. And so one of the most standard approaches, remember, for supervised learning with histopathological images is simply to take each tiny patch of this histopathological image and convert it into a representation by running a ResNet. And so a ResNet is a popular neural network that has been pre-trained on a data set of images, of general purpose images that have nothing to do with histopathology. And it's often a convenient pre-processing step because what you can do is take a ResNet that's been pre-trained on ImageNet and use it as a feature extractor. That is, use it to simply get these representations of each tiny patch in the image and feed that into a multiple instance learning algorithm to make predictions from your histopathological image. But the idea that we wanted to explore was a slightly newer one, which is that of self-supervised learning. Now, the key difference between supervised learning and self-supervised learning is the fact that self-supervised learning makes use of no labels at all. The goal, the intuition you should have for this class of methods is to think of them as asking the question, without any labels, can I use intrinsic similarities and differences in my image sample alone to learn a good representation? And so Lipkov et al. And Seeger et al. Are both really good examples of work that have been done in the context of using self-supervised learning to learn representations of images from histopathological data. And so our work, Richard's and my work, builds upon recent work, such as the one that's cited below from the University of Toronto, actually, who showed that self-supervision yields really good general purpose representations of histopathological images. And so in our work, we wanted to study one of the newer forms of self-supervised learning that has been proposed in 2021. And so this is this work called Dyno, which was originally developed to build self-supervised representations to be used in large software companies like Facebook. And what we wanted to ask is, could some of the techniques that have been developed in that context be useful here? So the way that the algorithm works is essentially as follows. In the bottom left, you start with the entire H&E image, and you take two different views on the image. So you could take a crop from the top left and a crop from the top right, and those could be your view. You could take the entire image and change the color contrast, and those could be your two views. And so this notion of data augmentation is effectively one that changes the underlying data that is being presented to the model, but does not change the meaning of the information that is in that image. So the idea is to present these two different views of the same image to two different networks that are then going to make a prediction about whether or not these images X1 and X2 are originally from the same image. And so they're going to print out a probability P1 and P2. And Dyno is an example of a network that essentially takes these two crops and predicts the likelihood of coming from the same image. And so the output of this student network on the left is trained to match the distribution of the teacher network via the minimization of a cross entropy loss or a log likelihood loss. And the way that this class of models avoids the collapse of a network to the identity representation, which is a common pathology if you were to train this network naively, is that the student is trained via gradient descent, but the teacher is not trained at all. So the teacher's weights are simply updated via an exponential moving average from the student. And what that means is you simply take the student's weights from a few time steps ago and propagate it forward to change and modify the teacher's weights. This seems like a very strange learning algorithm, and I think there's a lot to understand theoretically about why this works. But practically, it's been shown to work remarkably well. And one of the key differences between this approach and many different other self-supervision approaches is the fact that it does not require negative samples. And what that means is traditional approaches to self-supervised learning. Remember, self-supervised learning does not make use of labels, but it does use this idea of similar and different images and compares them to learned representations. And so this requires no comparison points. It's effectively creating artificial comparison points via data augmentation. And so the encoder that is used in Dyno is an example of a vision transformer, which is another new class of neural architectures that have been used for images before, but I think in the context of histopathological image analysis have not seen a lot of use. And so this is something that we wanted to experiment with in our work. So to quantify whether we are learning anything interesting, we're going to evaluate our models on the TCGA lung cohort. And so the TCGA is the Cancer Genome Atlas, which is a very large and freely available data repository of histopathological images that have been released to the public for analysis. And so there's about 12,000 patients, and the lung cohort is about, I believe, 2,000 to 3,000. And so you have 2,000 to 3,000 whole slide level slides of individuals who suffer from lung cancer. And within lung cancer, there's an enormous heterogeneity in the patient population. So you have some who have adenocarcinomas, squamous cell carcinomas, large cell carcinomas, as well as small cell lung cancer. And what we wanted to do is use machine learning algorithms like Dyno that I showed you in the previous slide in order to take a whole slide level image and come up with a single vector representation of that image. So even if you might have zoned out in the last few slides of this talk, that's okay. Our goal is to take an image of this of an individual who suffers from one of these cancers and come up with a vector of numbers. And we're going to evaluate how well this vector of numbers actually is as a quality by evaluating the way in which you can quantify LUAD versus LUSC, which is whether or not you can identify the subtype of lung cancer that the patient suffer from, whether you can use the representation as a feature function to then go on to do survival analysis, and whether or not you can detect genetic mutations from this representation effectively. And so the first set of results that I'll point to is here. And at the top left and the top right are examples of whole slide level images that come from patients from LUAD or LUSC, respectively. And on the bottom is our evaluation of how well our method does in the context of extracting representations, which when used for making predictions, have a certain amount of accuracy. And so we're looking at the accuracy on a held out set. So this is the test accuracy of each of these methods. So each row is a different method, and Dyno is the one that we investigated. When it talks about lung cancer only, it's talking about it in the context of just 2 different kinds of lung cancers. And so what we varied here was the number of training samples that we used in order to make predictions. So remember, the pipeline is we do self-supervised learning to get a representation of each whole slide level image. And then we vary the amount of training samples that are used in order to make predictions from the whole slide level representations that we got in the previous step. And so 100% denotes the use of the entire training sets for training. 25% says that we only use 25% of the labeled examples on the representations from self-supervised learning in order to do predictions. And that's what I'd like to draw your attention to. Because what the results show is that the representations from Dyno that we investigated seem to hold up remarkably well, even when we're using a quarter of the labeled examples to make predictions on the task of LUAD versus LUSC. And so they suggest that these self-supervised feature extractors from Dyno are very data efficient, more so than existing approaches that simply make use of pre-trained ResNet 50 models from ImageNet for subtyping. However, a limitation that I think is important to keep in mind is that we don't see the same transfer of results in the context of predicting something like genetic mutations like TP53 or KRAS. And so on this task, we did not find any interesting difference from the use of Dyno, although it does perform comparably well to many of the other alternative approaches. And finally, the third result, and so this is work in preparation, and so we'll have this out soon for all of you to read, is the fact that we did introspect into how the attention mechanisms in Dyno were making use of information in the images when creating these representations. And effectively what we found, and to me this was one of the most interesting results, was that different parts of the model were making use of different kinds of information about cellular substructure in composing this representation. For example, attention head 1 learned to focus exclusively on red blood cells. Attention head 2 focused exclusively on the location of the cells. And attention head 3 seemed to be focusing on the kinds of cytoplasm that existed between these cells. And so this introspection into how the self-supervised learning model was making decisions and constructing these general purpose representations give us a glimpse into the kind of information that's relevant and what's crucially different from what ResNet already captures. And so on the very right is the ground truth cellular segmentation, which the model did not have access to. And so all of the segmentations that you see in the middle in red are learned automatically via self-supervised learning. And so the key takeaway from this work really is that we have a lot of work to do to understand why the representations from self-supervised learning differ from those of ResNet and SimClear, and we hope to be able to release these models to the research community to study some of the properties that we simply may not have enough time to study on the TCGA data. And so we have about 4 minutes left, and I'll slowly start wrapping up now. I think that one of the key things that these two projects have taught me is to think harder about a modular approach for machine learning in healthcare. The reality is, for chronic diseases, clinical decision-making is often guided by multiple data modalities. No one is only going to look at a single tissue slide and determine the entire course of a patient's timeline. They're going to look at multiple sources of data modalities, such as their lab values, as well as their imaging data. And so in machine learning right now, we often train a new model for each task, potentially from scratch. And the concern that I have is that this ends up wasting a lot of repetitive predictive patterns that exist across tasks, and we don't make use of that very efficiently. And so the proposal that I've been thinking through is how to think of models as serving as effective proxies for tasks. So can we work in a paradigm where we train different unsupervised or self-supervised models to extract relevant patterns from each modality and treat that model as a unit and as something that gives us these general purpose representations that then we can go on to use for multiple different new tasks without having to retrain on all of the previous tasks. And so to this end, there are some technical challenges that need to be solved in order for us to get there. We need to go from our tool set that makes correlational predictions to one that makes causal predictions. And so this is sort of a summary list of some of the projects that we have ongoing in the lab right now, which is thinking about new algorithms to make use of causal graphs for density estimation, leveraging deep generative models as flexible structural equation models to answer counterfactual queries. In the context of deploying machine learning algorithms, one of the fundamental hurdles that people have to face is the fact that the data distribution often changes. How patients behave and how that behavior manifests in clinical data today is not going to look like what it was 10 years ago, and it's not going to look the same 10 years into the future. And so we need mechanisms to identify and detect when our models have become stale so that we can think about ways to retrain them. And finally, an approach that we've been thinking through is how to automate the discovery of risk scores. And so with Mamta Bhatt, who's a clinician at UHN, we've been thinking together about how to rethink scores for characterizing the risk of dying on a waiting list, waiting for a liver with something like the MEL sodium scores, and thinking about, is that fair? And does that work equally well across subgroups and genders and races? And we've been exploring the use of ideas in machine learning to automate the creation of interpretable risk scores to aid in clinical decision making. And so one of the reasons that I think it's important to think about this slide is it's asking, why should we care about using all of this data to find meaningful solutions to clinical problems? And I think the biggest pitch that I have for everyone in this audience here is that ultimately we're the ones who pay for healthcare and its costs continue to increase. And so the challenges that I talked to you about 2 slides ago were technical, but the reality is there's also some immense logistical hurdles that hold us back. We have issues like data silos and institutional barriers that we need to reduce. There's an opportunity cost issues, which is essentially that if the time that it takes for a master's student to get access to data is about a year, then they're simply going to look elsewhere for working on interesting problems. We need support for mechanisms that put data and high performance compute together, as well as support for both hypothesis-driven and exploratory research. Because at the end of the day, if you think about something like the TCGA, the NIH in 2006 had no idea what deep learning was because people weren't using it back then when they put out this giant data set of histopathological images and genetic data and we're reaping the benefits of their decision to do so right now. And so for this community, I encourage you all to think about some of the consequences of decisions that have been made in the past and the success stories that have emanated from it to try and think about how to structure the future of this field. And so I'll end with this plot, which is essentially that if you map all of the things that we know and what we don't know, I think a lot of the really interesting applied and methodological work happens in the space of unknown unknowns. And we have no idea what will happen. We'll react when it's needed, but essentially we should not be afraid of it. And we should come up with safe and secure mechanisms that allow people to experiment with clinical data to think about how to apply some of the latest tools that have been developed in fields, not just in machine learning, but also in econometrics and biostatistics, so that they can solve interesting problems that people didn't know they had. And so with that, I'll end. Thank you all so much for your time, and my apologies for going about a couple of minutes over, and I'm happy to take questions.
Thank you so much, Dr. Krishnan. Actually, I really want to thank you for an incredible talk, and I think you've addressed a few questions during your talk. We'd love to take a few questions. The only problem is we have a group of students now waiting for you. So what we'll do is, if everyone is okay, we'll end here. Please do feel free to reach out to Dr. Krishnan or the Temerty to T-CAIREM team if you have any follow-ups or any questions. And I just want to remind those students who are participating in the meet and greet to log into the meet and greet Zoom link. So there's a separate Zoom link for that. So please log in there. And please update by following us on Twitter and subscribing to our mailing list on our website, which is tcairem.utoronto.ca. So again, thank you so much, Dr. Krishnan, and thank you to everyone who attended. And we'll see you at the next speaker series round. Thank you. Take care, everyone.
Thank you.